Good day, everyone. For today, I will be discussing with you equations with homogeneous coefficients. Solution of the first order ordinary differential equations which are found to be homogeneous DE. First of all, let us define first what are homogeneous polynomials. These are polynomials where all terms have the same degree in all the variables present. Here are some examples. 4x squared minus 3xy plus y squared. As you can see, the first term having x squared, that is second degree in x. Our second term, first degree in x, first degree in y, making it also a second degree term. And the third term is second degree in y. So the first example is a polynomial of degree 2. Second example, 3x cubed plus 2y cubed. So both of them are of degree 3. On the third example, you have 2x cubed y. This is third degree in x and 1 degree in y, making it 4 degree. And you have second degree in x and second degree in y, making the term also degree 4. So example number 3 is a polynomial of fourth degree or degree 4. There are some terms of the differential equation in which you cannot do uh, or you cannot evaluate whether it is homogeneous or not by simple inspection. So what you have to do is to test the degree of homogeneity of the terms of the differential equation. The function f of x and y is said to be homogeneous of degree k if and only if a function of lambda x and lambda y is equal to lambda to the k times the given function of x and y. Let us have the following examples and let us determine if the following are homogeneous or not. If they are homogeneous, then let us give the degree of homogeneity. Example number 1. So you have here a function of xy is equal to 4x squared minus 3xy plus y squared. So we can actually do this by inspection. But to show you the test for homogeneity, we have to take the function of lambda x and lambda y, meaning you replace all x by lambda x and all y by lambda y. So this is 4 lambda x quantity square, minus 3 times lambda x, lambda y, plus lambda y quantity square. Let me just erase this. Okay? And then, simplifying, this is 4 lambda square x squared minus 3 lambda times lambda is lambda squared xy plus lambda square y square. And all of the terms consist of lambda square. So we can factor out lambda square times x squared minus 3xy plus y squared. And this is simply equal to lambda square times the given function of x and y. Oh, I forgot here the 4. Sorry. You have here 4. So you have here 4x squared. Okay? So this is now your original function for x squared minus 3xy plus y squared. And this is your lambda squared. Therefore, based on the previous slide, this is homogeneous of degree 2. Therefore, this is homogeneous of degree 2 because of this lambda to the k. Okay, number 2 problem. Determine whether function of x and y, let's put it here, the function of xy is equal to x ln of x minus y ln of y. So taking function of lambda x and lambda y that is equal to lambda x ln of lambda x minus lambda y ln of lambda y. So we can factor out lambda times x ln of lambda x minus y ln of lambda y. Can we still factor this out or simplify this one to make it x ln x minus y ln y? So if not, then therefore, this is not homogeneous because we cannot express the function of lambda x and lambda y in terms of lambda to the k times the original function of x and y. Then we have problem or example number 3. Determine whether the function, number 3, the function of x and y is equal to tangent of the quantity 3x over y. So function of lambda x and lambda y that is equal to tangent of 3 lambda x over lambda y. So lambda over lambda. And therefore, this is equal to tangent of 3x over y, which is actually equal to the original function of xy. So this is actually equal to lambda to the 0, tangent of 3x over y. Or this is lambda to the 0 times the given function. Therefore, this is homogeneous of degree 0. Okay? Then let us take number 4, if that is homogeneous or not. Problem number 4, function of xy is equal to 2y cubed e to the y over x. Okay? Minus x to the 4th over x plus 3y. So let us take the function of lambda x and lambda y. That is equal now to 2 lambda cube y cube e to the lambda x over lambda y, sorry, over lambda x minus lambda to the 4th x to the 4th over lambda x plus 3 lambda y. So this is now equal to 2 lambda cube y cube, and this one is e to the lambda y over lambda x, so lambda over lambda, e to the y over x minus, this is lambda to the 4th over times x to the 4th over, common here is lambda. So you have here lambda to the 4th, x to the 4th over lambda times x plus 3y. So this is now equal to 2 lambda cube y cube e to the y over x minus, so lambda to the 4th over lambda is lambda cube. X to the 4th over x plus 3y. So you have here lambda cube and lambda cube, so we can factor out lambda cube times 2y cube e to the y over x minus x to the 4th over x plus 3y. And this is simply lambda cube times our given function of x and y. So you have 2y cubed e to the y over x minus x to the 4th over x plus 3y. So this is again our function of lambda x and lambda y. And therefore, the given function is homogeneous of degree 3. That is the test for homogeneity. If the given terms of the differential equation can be evaluated whether it is homogeneous or not by inspection, you can do actually by inspection. But for those terms with transcendental functions, it is necessary for you to do the test for homogeneity. Okay? Here are some of the theorems that will help us to provide the solution of homogeneous differential equation. If m as a function of x and y and n as a function of x and y are both homogeneous of the same degree, then we take the ratio of m and n, then that ratio is also homogeneous of degree 0. Another theorem, number 2, is that if the function of x and y is homogeneous of degree 0 in x and y, then the function of x and y is a function of y over x alone. Now, how are we going then to solve or to provide solution to a differential equation which is found to be homogeneous? So suppose that m and n in the differential equation of the first order, m as a function of x and y dx plus n as a function of x and y dy equals 0, are both homogeneous and are of same degree in x and y, then we can form this equation. Derivative of y with respect to x plus m over n is equal to 0. And using the above theorems, we can put that in this form of derivative of y with respect to x plus a function of y over x is equal to 0. And from this, we may introduce a new variable v such that y is equal to vx. So that is actually the solution or the start of the solution of a homogeneous differential equation. We are going to introduce a new variable, let us say v, to be equal to, or v is to be introduced in a manner that we let y to be equal to vx, or it can be x is equal to vy. If we are to use y equals vx, then the equation becomes x derivative of v with respect to x plus v plus a function of v is equal to 0. And this equation now is actually a separable equation. I have here some examples to illustrate to you the solution of a homogeneous differential equation. So let us take example number 1. Solve the differential equation 2 times 2x squared plus y squared dx minus xy dy is equal to 0. Okay? So by inspection, we can see here that the differential equation is homogeneous of degree 2. We have here x squared, y squared, and then you have 1 degree in x, 1 degree in y, also a second degree term. So this is a homogeneous differential equation of degree 2. So let us proceed with the solution. We start with introducing the new variable. Let y it is equal to vx. V here is a new variable. So when you take its dy, you will be taking here the derivative of product v dx plus x dv. Then we need to substitute it to our given differential equation. Okay? So let us distribute also the 2 here and the given differential equation. So you have there 4x squared plus 2y squared, but our y is vx. So that is now equal to 2v squared x squared dx minus x. Our y is vx and our dy now is v dx plus x dv is equal to 0. Then we simplify the equation. This is now 4x squared dx plus 2v squared x squared dx. Then we multiply this minus x, vx, and v. So we have minus v squared x squared dx. Then minus x, vx, and x dv. So that is minus v x cubed dv is equal to 0. Okay? And then combining like terms, you have here on the second term 2v squared x squared dx, and you have here negative v squared x squared dx. So subtracting the two, you have v squared x squared dx. So the resulting equation now, 4x squared dx plus v squared x squared dx minus v x cubed dv is equal to 0. And from the first two terms, you can factor out x squared and dx. So you have x squared times 4 plus v squared dx minus v x cubed dv is equal to 0. The resulting equation now is a separable equation. So how can we separate x from v? We divide both sides of the equation by those factors not needed in the term, 4 plus v squared and x cubed, which resulted now to dx over x minus v over 4 plus v squared dv is equal to 0. And now we integrate all terms of the equation. First term, integral of dx over x is ln of x. Second term, here you have v dv, and on the denominator you have 4 plus v squared. So if you let u to be 4 plus v squared, our du is 2v dv. But the numerator is only v dv, so that is simply minus 1 half ln of 4 plus v squared is equal to integral of 0c or ln of c, since the left terms contains ln. Okay? And then we multiply first it by 2 to eliminate the numerical coefficient, which is a fraction. So this is 2 ln of x minus ln of 4 plus v squared is equal to 2 ln c. That is also still equal to ln of c. ln of c or 2 ln c is still c. Okay? And then here we apply the property of natural logarithm. 2 ln x is ln of x squared. And then you have minus here, so that is ln of quotient. ln of x squared over 4 plus v squared is equal to ln of c. And then we take base of both sides, and you now have x squared over 4 plus v squared is equal to c. But this is not yet our solution because we have here v, and initially our variables are x and y. So we need to replace v by the original variables x and y. So from this, when we let y equals vx, then v is equal to y over x. So we substitute it here. So x squared over 4 plus y squared over x squared is equal to c. Okay? And then simplifying, what will then be our result? So you have x squared is equal to c times 4x squared plus y squared over x squared. Or cross multiplying, you have x to the fourth is equal to c times 4x squared plus y squared. So that is now the solution of the homogeneous differential equation. So take note that here I used let y is equal to vx. It is your task to try the other variable x is equal to vy. So try let x is equal to vy and your dx is equal to v dy plus y dv. So you just need to do the same process. You should be ending up with a variable separable equation, and do not forget to bring back the original variables x and y. And you should be also obtaining the same result of x to the fourth is equal to c times 4x squared plus y squared. Okay? Now let us have another example, number 2. Again, the first thing that you have to do is to test whether the given differential equation is homogeneous or not. Because the procedure that we are talking here is applicable only for homogeneous differential equation. So let us try having this one. Let us do by inspection. So as you can see here, the second term of the differential equation is x. So it is first degree or degree 1. This term is y, so this is also degree 1. So we are just need to take a test for homogeneity for this term. You have here x. So when you take lambda x, so that would be lambda x. And for this one is lambda y over lambda x. So lambda over lambda, that will make again y over x. So lambda x minus lambda y minus, plus lambda x. So we can factor out lambda. So lambda to the 1 times this function actually. So therefore, this differential equation is homogeneous of degree 1. So let us now solve this differential equation. If we use let y is equal to vx, then our dy again, derivative of product v dx plus x dv. So we substitute it here. That would be x cosecant of our y is vx over x minus vx times dx plus x times v dx plus x dv is equal to 0. Okay, so simplifying the equation, this is x cosecant of v dx minus vx dx plus vx dx plus x squared dv is equal to 0. So negative vx dx and positive vx dx, that is 0. Remaining now is x cosecant of v dx plus x squared dv is equal to 0. And we can separate the variable x from the variable v by dividing it by cosecant of v and x squared. And resulting now is dx over x plus dv over cosecant of v is equal to 0. And we know that 1 over cosecant is sine. So plus sine v dv is equal to 0. And now we can integrate both sides of the equation. Okay, so integrating, you have ln of x, integral of sine is negative, cosine of v is equal to integral of 0. Let us use ln of c since we have here ln of x. Okay? So we have ln of x minus ln of c is equal to cosine of v. And property of ln, so you have here ln of x over c is equal to cosine of v. But again, what is v? But v is equal to y over x. So you have ln of x over c is equal to cosine of y over x. Okay? So that is now the solution of our given differential equation. X cosecant of y over x minus y dx plus x dy equals 0, which is a homogeneous differential equation of degree 1. Let me give you a third example, but this time let us use different variables s and t. Excuse me. Okay? So instead of having y and x, we use now s and t. So we are still to use or to introduce a new variable v. Let us inspect first. So the first term is ts squared, so third degree. Second term, t cubed, so third degree. S cubed, third degree. The next term is st squared, so that is third degree. So this is homogeneous differential equation, degree 3. So let us take, let S, we take, let S is equal to V times T. And therefore ds is equal to V dt plus T dV, derivative of product. So we substitute it here. So you have T times our S is Vt, so that is V squared, T squared plus T squared times ds is V dt plus T dV minus, so that is S cubed, so that is V cubed, T cubed dt plus our S again is Vt times T squared, so that is V T cubed dt is equal to 0. Okay, so let us now simplify. This term times this. So that is V cubed T cubed dt. Then this term times this. That is V squared T to the fourth. Is it correct? V squared, then T cubed, and then another T. So plus V squared T to the fourth dV. And then this term plus V T cubed dt. Then plus T to the fourth dV minus these two terms, V cubed T cubed dt plus V T cubed dt is equal to 0. Okay? And now combining like terms. You have here V cubed T cubed dt and negative V cubed T cubed dt. So this is 0. And then common to this V squared T to the fourth dV and T to the fourth dV is T to the fourth dV. So you have T to the fourth times V squared plus 1 dV. Then you have here Vt cubed dt and Vt cubed dt. So you have plus 2V T cubed dt is equal to 0. And now separating the variables t from v by dividing it by t to the fourth and v. Okay? So resulting equation now, v squared plus 1 over v dv plus 2 over t dt is equal to 0. Okay? And then, we now integrate both sides of the equation. So how do we integrate the first term? We divide it first. So that is v plus 1 over v dv plus 2, the integral of dt over t is equal to the integral of 0. So integral of v dv is v squared over 2 integral of dv over v plus ln of v plus 2 ln of t is equal to ln of c. Okay? And then, we may now substitute our v. What is v? But v is equal to s over t. So we now have s squared over 2t squared plus ln of v. So that is ln of s over t plus 2 ln of t is equal to ln of c. So here, this is also equal to what? So s squared over 2t squared plus, this is simply the difference of 2ln. So this is ln of s minus ln of t plus 2 ln of t. We can put also ln of c on the left side. Ln of c, negative ln of c is still c. Let me use plus ln of c is equal to 0. So you have here negative ln t and 2 ln t. So remaining now is s squared over 2t squared plus ln of the product s, t, and c. So s, t, or c, s, t is equal to 0. Or you may say that s squared over 2t squared is equal to negative ln of c, s, t. And that is now the solution of this differential equation. So later, you may try again using, you let the other variable t is equal to vs. And your dt would be vds plus sdv. And you should be obtaining the same solution. Okay, so those are the three examples that I can share with you for the solution of homogeneous differential equation. Hope that you have learned something from this video. Thank you.